Radiation, pressurized environment, and thermal stress hazard. In this topic, we will focus our discussion on the radiation hazards, pressurized environment hazards, and thermal stress hazards. Radiation hazards. Radiation is the energy that radiated or transmitted in the form of waves or particles. Radiation hazards in the workplace fall into two categories: ionizing radiation or non-ionizing radiation. An ion is an electrically charged atom or groups of atoms that becomes charged when a neutral atom or group of atoms loses or gains one or more electrons as a result of a chemical reaction. If an electron lost during this process, a positively charged ion is produced. If an electron is gained, a negatively charged ion is produced. Thus, we can say that to ionize is to become electrically charged or to change into ions. Therefore, ionizing radiation is radiation that becomes electrically charged or changed into ions. All forms of ionizing radiation have sufficient energy to ionize atoms that may destabilize molecules within cells and lead to tissue damage. Meanwhile, non-ionizing radiation is essential to life. However, excessive exposures to the non-ionizing radiation may cause tissue damage. Note that radiation sources may be found in a wide range of occupational settings. If the radiation is not properly controlled, it can be potentially hazardous to the health of the workers. Non-ionizing radiation is the electromagnetic radiation that ranging from extremely low frequency ELF to ultraviolet. Ionizing radiation can be divided into two types: particulate radiation including alpha, beta, and neurons, and electromagnetic radiation such as X-rays and gamma rays. These are the common sources of radiation in our daily lives: telephones, navigation, cooking and heat, and medical scanners having different types of waves. Here are the types of non-ionizing radiation. Extremely low frequency ELF radiation at 60 Hz is produced by power lines, electrical wiring, and electrical equipment. Common sources of intense exposure include ELF induction furnaces and high voltage power lines. Radio frequency and microwave radiation. Microwave radiation (MW) is absorbed near the skin, while radio frequency RF radiation may be absorbed throughout the body. At high enough intensities, both will damage tissue through heating. Sources of RF and MW radiation includes radio emitters and cell phones. Infrared radiation. The skin and eyes absorb infrared radiation as heat. Workers will normally notice excessive exposure through heat sensation and pain. Sources of infrared radiation including furnaces, heat lamps, and infrared lasers. Visible light radiation. The different visible frequencies of the electromagnetic spectrum are seen by our eyes as different colors. Good lighting is conducive to increased production and may help prevent incidents related to poor lighting conditions. Excessive visible radiation can damage the eyes and skin. Ultraviolet radiation. Ultraviolet radiation (UV) has a high photon energy range and is particularly hazardous because there are usually no immediate symptoms of excessive exposures. Sources of ultraviolet radiation include the sun, black lights, welding arcs, and UV lasers. Laser hazards. Lasers typically emit optical, such as ultraviolet, visible light, and infrared radiations, and are primarily an eye and skin hazard. Common lasers include carbon dioxide infrared laser, helium neon, neodymium, YAG, and ruby visible lasers, and the nitrogen ultraviolet laser. Ionizing radiation consists of energetic nuclear particles and includes alpha rays, beta rays, gamma rays, X-rays, neutrons, high-speed electrons, and high-speed protons. Ionizing radiation can be normally found in healthcare facilities, research institutions, nuclear reactors and their support facilities, nuclear weapon production facilities, and other various manufacturing settings. A measure of the dose of ionizing radiation to body tissue stated in the terms of its estimated biological effect relative to a dose of 1 Roentgen of X-rays is called RAM, while RAD is a measure of the dose of ionizing radiation absorbed by body tissues stated in terms of the amount of energy absorbed per unit mass of tissue. 1 rad equal to the absorption of 100 ergs per grams of tissue. The exposure of employees to radiation must be carefully controlled and accurately monitored. This figure shows the maximum doses for individuals in 1 calendar quarter. Employers are responsible to ensure that these dosages are not exceeded. However, there are exceptions to the amounts shown in this figure. For this, you may need to refer to Occupational Safety and Health Administration guidelines on the conditions allowed. Personal monitoring precautions are important for employees of companies that produce, use, release, dispose of, or store radioactive materials or any other sources of ionizing radiation. Some of the precautions that required by OSHA are employers must conduct comprehensive surveys to identify and evaluate radiation hazards present in the workplace from any and all sources. Employers must provide appropriate personal monitoring devices such as film badges, pocket chambers, pocket dosimeters, and film rings. In order to minimizing the ionizing radiation hazards, we may consider these precautions that limit the exposure to the radioactive material, such as use low-level radioactive material, keep a minimum exposure time, stay as far from the radiation source as possible. If the distance is doubled, the exposure is reduced by a factor of 4. Monitor the radiation levels throughout the time of exposure with the use of gauge counter and store the material in a suitable shielded container. For example, keep the lead storage pod in a properly marked cabinet that is not frequently used by people. Pressure hazards. We all know that pressure is defined as the force exerted against an opposing fluid or thrust distributed over a surface. Pressure is expressed as force or weight per unit area, such as Newton per square meter or pounds per square inch (psi). For your information, critical injury or damage can occur even with relatively little pressure. One of the laws related with pressure is Boyle's law, where the product of a given pressure and volume is constant in an isothermal condition. Pressure also plays a role in human respiratory system. The air moves in and out of the lungs is due to pressure gradient or difference in pressure. When the atmospheric pressure is greater than pressure within the lungs, the air flows from the ambient into the lungs. This is called inspiration, inhalation, or breathing in, and occurs with greater lung volume than at rest. When the pressure in the lungs is greater than the atmospheric pressure, the air will move from the lungs to the ambient. This scenario is called expiration, where the air leaves the lungs and the lungs volume is less than the relaxed volume, thus increasing pressure within the lungs. There are many sources of pressure hazards, where some is due to natural occurrences, but most were created by humans. Because the human body is made up of 85% liquid, which virtually considered as incompressible, increasing pressure does not create problems by itself. Problems can result from air being trapped or expanded within body cavities. When sinus passages are blocked, the air cannot pass easily from the sinuses to the nose. Expansion of the air in these sinuses can lead to problems. The same complication can occur with air trap in the middle ear's eustachian tube. As Bosch's law states that gas volume increases as pressure decreases, the expansion of air in the blocked sinus passages or the middle ear occurs with a rapid increase in altitude or rapid ascent underwater. This can cause pain and, if not eventually relieve, disease. Under extreme circumstances of rapid ascent from underwater diving or high altitude decompression, the lungs can rupture. At sea levels, the average Earth atmosphere is 760 mm mercury or 14.1 psi, depending on the measuring scale used. Barometer is a device to measure the atmospheric pressure. As the altitude increases, the atmospheric pressure decreases in a non-linear fashion. Boiler and pressure hazards. A boiler is a closed vessel in which water is heated to form steam, hot water, or high temperature water under pressure. Potential safety hazards that associated with boilers and other pressurized vessels, including design, construction, or installation errors, poor or insufficient training of operators, mechanical breakdown or failure, failure or blockage of control or safety devices, insufficient or improper inspections or preventive maintenance, and improper application of equipments. High temperature water hazards. High temperature water is water that has been heated to very high temperature but not high enough to produce steam. There are hazards associated with high temperature water. If any person is in contact with this high temperature water, they can get extremely serious burns and in some cases even death. Two most prominent sources of hazards related with high temperature water are operator error and improper design. Proper training and careful supervision are the best guard against operator error. Design of high temperature water systems is highly specialized process that should be undertaken only by experienced engineer. Mechanical forces such as water hammer, thermal expansion, thermal shock, or faulty materials cause system failures more often than the thermodynamic forces. Therefore, it is important to allow for such causes when designing a high temperature water systems. The best designs are simple and operator friendly. Avoid designing too many automatic controls into an high temperature water system, which can create more problems than it solves by turning operators into a person that unable to respond properly during the emergencies. For your information, water hammer is a shock effect that caused by liquids flow that suddenly stops and produce loud noise. The momentum resulted by this scenario will conducted back to the upstream in a shock wave. This may damage the piping system, including the pipe fittings and valves. To reduce this hazard, air chambers is usually installed in the system and the use of quick closing valve is avoided. Not all pressure vessels are fired. Unfired pressure vessels include compressed air tanks, steam-jacketed kettles, digesters, and vulcanizers, and others that can create heat internally by various means rather than by the external fire. The various means of creating internal heat including chemical action within the vessel and application of some heating medium such as electricity, steam, and hot oil to the contents of the vessel. The potential hazards associated with unfired pressure vessels are hazardous interaction between the material of the vessel and the materials that will be processed in it. Inability of the filled vessel to carry the weight of its contents and the corresponding internal pressure. Inability of the vessel to withstand the pressure introduced into it plus pressure caused by chemical reactions that occur during processing. And inability of the vessel to withstand any vacuum that may be created accidentally or intentionally. One of the most serious hazards in pressure vessel is the potential of cracking. Cracking can lead to either complete rupture or to leaks. The consequences of complete rupture including blast effects due to the sudden expansion of the contents of the vessels and possible injuries and damage from fragmentation. Meanwhile, the consequences of a leak may include suffocation or poisoning of employees, which depends on the contents of the vessel, explosion and fire, and chemical and thermal burns from contact with the contents of the vessel. Pressure vessels are used in many different applications to contain many different types of substances from water to extremely toxic chemicals. Leakage or rupture may occur in welded seams, bolted joints, or at nozzles. To prevent leakage and rupture, it is necessary to examine the pressure vessels periodically. There are 5 widely used non-destructive methods for testing: visual examination, liquid penetration test, magnet particle test, X-ray radiography, and ultrasonic tests. Visual, liquid penetration, and magnetic particle tests can detect only defects on or near to the surface. Thus, they are referred to as surface tests. Meanwhile, radiographic or ultrasonic tests can detect problems within the material. Thus, they are called volumetric tests. These are several methods to reduce the hazards associated with pressurized containers. Please have a look at this list. Thermal stress hazards. Thermal stress can be defined as the physical and physiological reactions of the human body to temperatures that falls outside of the normal comfort zone. Thermal comfort in the workplace is a function of a number of different factors. Temperature, humidity, air distribution, personal preference, and acclimatization are all the determinants of comfort in the workplace. However, determining optimum conditions is not a simple process. For example, a work environment that not properly control the temperature can be uncomfortable. Extreme heat or cold can be more than uncomfortable, which is dangerous. Thus, modern safety and health professionals are concerned about heat stress, cool stress, and burns. Heat stress is the net heat load to which a worker may be exposed from the combined contributions of metabolic effect of work environment factors such as the air temperature, humidity, air movement, and radiant heat exchange, and clothing requirements. A mild or moderate heat stress may cause discomfort and affecting the performance and safety, but it is not harmful to health. However, as the heat stress approaches human tolerable limits, the risk of heat-related disorders increases. What follows are some widely used heat stress-related terms that we should be familiar with. Heat exhaustion. This is a physical state in which skin becomes clammy and moist, and body temperature is still normal or slightly higher than normal. Heat exhaustion results from fluid and salt loss through sweating that are not properly replaced during exertion. Heat stroke. This is a physical state which the skin becomes hot and dry. There is mental confusion, and there may be seizures or convulsions. Heat cramps are muscle cramps that can occur when workers exert themselves sufficiently to lose fluids and salt through sweating, but replace only fluids by drinking large amounts of water containing no salt. Heat rash. Workers who in a hot environment in which sweat does not evaporate can develop a prickly rash known as heat rash. Periodic rest breaks in a cool environment that allows sweat to evaporate will prevent heat rash. American Conference of Governmental Industrial Hygienists (ACGIH) recommends the following specific controls in heat stress management. Establish engineering controls that reduce metabolic rate, provide general air movement, reduce process heat and water vapor release, and shield radiant heat sources. Consider administrative controls that set acceptable exposure times, allow sufficient recovery, and limit the physiological strain. And consider personal protection that has been demonstrated to be effective for the specific work practices and conditions at the location. Cool stress. Excessive exposure to cool can lead to hypothermia, which can be fatal. Excessive exposure to cold stress, even when not fatal, can result in impaired judgment, reduced alertness, and poor decision making. Acute cold stress can cause reduced muscular function, decreased tactile sensitivity, reduced blood flow, and thickening of the synovial fluid. Chronic cold stress can lead to reduced functioning and peripheral nervous system. All these factors increase the likelihood of accidents and injuries. When work is to be performed in an environment with an air temperature of 4 degrees Celsius or less, total protective clothing is advisable. Other strategies that can be used to decrease the hazards of cold stress are: when heavy work is necessary, employees should take frequent warming breaks in heated shelters. If clothing becomes wet, internally or externally, it should be changed during a break. When working in a cold setting, use auxiliary heat applied directly to the hands and feet. Use facial protection to prevent cool stress to the face and lungs. Never use unprotected metal chairs or seats. Make sure employees working in a cool environment have been trained in safety and health procedures. Guidelines on Heat Stress Management at Workplace 2016 provide the guidance on how to recognize, estimate, prevent, and treat heat stress at work. Parameters of heat stress are introduced in this guideline to guide employers in avoiding discomfort from hot environment at work. The guideline also elaborates on risk assessment and risk control based on heat stress estimation using wet bulb globe temperatures (WBGT). The employers have to take practicable measures to ensure employees are protected from excessive heat exposure while at work.